Hello and welcome to our next set of stats notes. We are starting our kind of second unit. We're done with our first exam. So the material for the second exam will start with the section we're covering today. It'll cover chapters 6, 7, and 8. So we're going to get through three more chapters, and then after that we'll be ready for the second exam. Chapter 6, we start off, we're going to talk about the standard normal distribution. We've talked about distributions before, these histograms distributions. They're charts that kind of show the data. We talk about how they could be unimodal, bimodal, they could have symmetry or not, that kind of stuff. Well, we're going to specifically talk about normal distributions in this section. Normal distributions are important to statistics because a lot of the different variables, a lot of the different things we study will turn out to be normal distributions. Things like test scores, heights, wheat yields, all that kind of stuff. It's going to end up when you collect the data and graph it, it'll look like this shape, a normal distribution. Normal distribution is going to be this curve like this. We call this bell-shaped because it does have a nice symmetry in the middle, right? So you can see there's a symmetry where it's symmetric over the middle. It's kind of flared out at the ends like that. So we call this a bell shape. It's unimodal, right? There's only one peak. So this is normal distribution is always going to be bell-shaped, which means symmetric and unimodal. It's going to be centered at the mean. Remember that we use the mu for mean. So it's always going to be centered at the mean. So the average is going to be right in the middle for normal distribution. And then it's going to get really close to the axis. It's going to really get close to zero for values more than 3 standard deviations away from mean. Remember that this little sigma here we use for standard deviation. So I start at the mean and I add a standard deviation, or I add 2, or I add 3. Well, I'm getting further and further away from the mean. And once you get past 3 standard deviations away from the mean, then values are going to be really, really rare. So that's going to be the last thing. 3 up or 3 down, values out there are pretty rare. And we kind of talked about before that once you get past 2 or 3 standard deviations, things get really rare. Remember we had that 68, 95, 99.7 rule. And we said that if you go out 3 standard deviations, you're going to have like 99.7% of the data. So in the middle, it's going to be like 99.7. That's a lot. That's almost everything. So the stuff that's left over, the results, that end up on these tails are going to be very, really rare. There's not going to be a lot of them. Most values are going to be kind of in the middle. That's a normal distribution, and there's lots of these. Most of the time, if you do deal with statistically studying things that have kind of different influences and stuff, you're probably going to end up with this normal distribution. So you should know it's symmetric. The two halves always match. It's unimodal, just one bump. It's centered at the mean. The mean is always in the middle. And then if you go past 3 standard deviations, left or right, then there's just not much left over. They have all kinds of shapes because the mean can be different. So like see this one has a mean of -2, so it's over here. This one has a mean of 3, so it's right here. Mean of 9, so that's why they're in different locations. Their standard deviation can be different. So this one has a very small standard deviation, which remember that measures the spread. So the spread for this one is very small, so it's not very spread out. It's kind of centered really closely. This one has a standard deviation of 1, so it's a little more spread out. And this one has a standard deviation of 2. It's got the highest standard deviation, so you can see it's the most spread out. So you can have all kinds of normal distributions. Each one's going to be, the shape is going to be based on its mean and standard deviation. Again, that's really what makes normal distributions important. We'll see throughout the section is because all you really need to know about a normal distribution is its mean and its standard deviation, and you can do a lot with that. You don't really need anything else because if you know it's normal, then you already know it's going to have a nice bell shape. It's going to be centered at the mean. All that kind of stuff is given to you, so it's going to be powerful. Now, before we get too much into normal distributions, I want to take a little sidetrack and talk about the area under distributions. And it's a little easier to go show an example of that using this uniform distribution. So we're going to use a uniform distribution to show the area under distribution. So a uniform distribution is a little more simple. It's not very common, but it's a nice simple example. Uniform distribution just means that the height is the same all the way across. So uniform is just spread out evenly over all the range of possibilities. That's going to be uniform. So you can see it's the same height all the way across. This one goes from values from 0 to 5. And its shape, yeah, it's a rectangle. It's a basic rectangle. Now, because the height is the same the whole time, and the height is based on the frequency of the values, you can actually find the area under this, and that area will actually correspond to the percentage or probability of values being in that range. So like if you find the area of values between 0 to 2, like if you find this area right here is actually going to correspond to the percentage of values that are between 0 to 2. And that's true for all distributions, not just this one, because the heights are always based on the frequency. This one's just uniform, so it's a little bit easier to work with. So for example, let's look at this example. You see it goes from 0 to 5, right? So the width is 5. And 100% of the data is in this, right? This is the whole chart, right? We're not missing a piece. It's the whole chart, so it holds 100% of the data. So if I take the 100% of the data we have, and I divide it by the 5 length this has, I can see that each piece is actually a 20% height, or you could call that 0.2. So this height actually needs to be 0.2 for this chart to make this show all the data. So the frequency here, the height would be 0.2, since this is 20%, that's 20%, that's 20%, that's 20%, that's 20%, and you add up those 20%, and you get the whole 100%. So the height is 0.2 right here. That's your frequency, that's your height, and it's based on that 100% being spread out across this whole thing. Now, if they ask us a question like, what probability or the percentage, remember the probability and percentage, we're going to kind of use interchangeably at this point. I'm going to do that a lot because the percentage of something is going to be the likelihood that happens. You know, 50% of the people have health insurance. What's the chance someone random has health insurance? It's going to be 50% because 50% of people do. So the probability is the same thing as asking for the percentage. We want the probability of something being between 2 to 5. So we're looking for this range from 2 to 5. Looking for this range. We want to figure out what is that area right there. Well, we just talked about the height being 0.2, and you can see this shape right here is a rectangle. So you can just take that 0.2 height times this length. You can find this area, because that's how we do rectangles, right? We find the area by doing the height. So we're going to do 0.2. And this is a length 3, right? Going down here from 2 to 5 is 3. We'll take 0.2 times 3, and we get 0.6, or 60%. So between 2 to 5, because it's a width 3, you know, that's a space of 3, and the 0.2 height, that's actually 60%. So we can see, you know, 20, 30, 40, 60% of the values are in that range. So what are the chances from this distribution? You pick a sample that's between 2 to 5, well, it's a 60% chance. 60% of the values are in that range. So this basic idea, this expands to any kind of distribution, not just uniform. Uniform is pretty easy to work with because it's a nice little rectangle, and that's why I wanted to show you how this kind of works. But statisticians took this idea and actually use it with normal distributions and other distributions. They say, okay, well, if I'm looking for what percentage of values are in a given range, I just take the chart and find the area of that piece. Once I have the area of that piece, then I know the probability or percentage of values being in that range. This is important for all kinds of situations. We'll see examples later dealing with trying to design things for people. You know, if I want a chair that 90% of people can use, then I gotta find the range that includes 90% of the average person's height, weight, or whatever I'm looking for. If I'm looking for, you know, what percentage of people score from a 70 to a 90 on a standard days test, then I'm going to, you know, find that range and finding a percentage. It's the same idea. So there's going to be lots of situations where we're going to find this area, which is a probability percentage for us, for a set of data. And we're really going to have to know about the mean, because remember, the mean is where the distribution will be centered for normal distributions, and the standard deviation. And using that, we'll be able to find lots of different things. That's what we're going to do the rest of the section. Do this kind of same idea of finding the area, the probability percentage with normal distributions. Okay. So, distributions are rarely uniform. I had a little typo there, so I had to fix that. It says I put normal, I meant to put uniform. So they're not usually uniform. They don't usually make that nice rectangle for us. Most of the time, the areas are going to be normal. They're usually going to be normal curves that we work with. So something like this. But we can still use the same idea, and we can find the area or percentage probability of a region of this to find out the percentage probability of values being in that region. So for example, in this picture, this area right here that's shaded is 22% or 0.22. So 22% of the results are in this area. The rest is going to be the rest of the data. Just a note, this would be 78% or 0.78, right? Because 100 minus 22 gives you 0.78. So 0.22 is this region down here. The rest of it 78 because it should always add up to 100% total. This curve has 100% underneath. Since this value cutoff right here is 48, so that's where the cutoff is, we can see that 22% of the value of the area is left of 48. That means that 22% of the values are below 48. So because 0.22 is the area left of 48, then 22% of the values are below 48. Conversely, we can say that 78% of values are above 48. So for this data set, if you look at the data, you'll find out 20%, 2% of the results, surveyed results or whatever, were below 48. The other 78% were above 48. That way, if you're saying, oh, what's the chances I pick a random test and, this is a test, I'm just making up a situation. Take a random test and say, what are the chances that the score is below 48? Well, there's a 22% chance. Or what are the chances it's above 48? Well, there's a 78% chance that's above 48. So by having a cutoff and finding this area, we can kind of talk about the probabilities of these kind of results. That's where we're going to be using this for. So we're going to find lots of areas. This is actually something that we'll do the rest of the semester, because we're going to find out that this finding areas on these curves is essential to a lot of statistics. A lot of statistics will involve this process of finding areas and parts of the curve. Now, to make this easier, because this is actually really challenging now. With the rectangle, it's really easy, but this is actually challenging because finding the area under a curve like this is actually a calculus problem. So it's actually a calculus problem. If I just give you a curve and say, hey, find the area left of 48, and you have to go find the area, that's really hard. It's a calculus problem. This is not a calculus class, so we're not going to do any calculus. So instead, we actually figured out a way to kind of make this simpler for ourselves. And so what we did is we took all the different random curves we could have. We kind of saw on the previous page how there was all those different type of normal distributions, and they all look different, and they'd be different problems. Well, what we do is we actually take those and we standardize them. Make them all look like the same one. You can just use a little calculation, which I'll show you on the next page, and we can take every normal curve we have and we can basically turn it into one nice standard curve. And this standard curve is a little simpler, and then because we're all using the same curve, we'll actually have tables and stuff that'll help us work with this curve. It'll avoid the calculus. So we're going to standardize. We will standardize. So we're going to transform each normal distribution into the standard normal distribution. Now, what is the standard normal distribution? Well, it's still a bell curve because it's still a normal distribution, but it's a nice bell curve that is centered at 0. It's nice to have 0 in the middle because when you have symmetry, remember all these bell curves have symmetry, then you have the nice symmetry of the ones, -1, 2, 3. The stuff on the left and right match, and they're the matching corresponding numbers, right? 1 and -1, 2 and -2, 3 and -3, those nice opposites. Also, you notice that I'm counting by ones here on the bottom. I'm actually counting by a standard deviation, because for the standard deviation, for our standard normal curve, the standard deviation is a nice even 1. So we're making things easier because now we get to work with a really nice mean. 0 mean is a really nice number, easy to number to work with, and we're going to work with a nice standard deviation of 1. So that way, when I have to figure out, things with this curve, the areas and all that, it's a lot simpler because we're working with nice, simple, easy numbers. That's what makes it a standard normal distribution versus just any normal distribution. Again, you could have normal distributions with a mean of, 5, 10, a million. We want to make a standard normal distribution because it's just simply easier to work with. So again, the middle number is going to be your mu, and then the standard deviation again is sigma. If we go 2 of them, that's 2 sigmas. And this would be 3 sigmas. So again, because the standard deviation is 1, the mean is 0, so we get to count out 1, 2, 3 instead of having to count out by 5s, 10s, or 20s, because the standard deviation could be any of those numbers, but we're going to make it simple. So we're going to take any curve they give us, any information they give us, and we're going to standardize it, make it nice and simple, before we start trying to find areas and stuff like that. Okay. So, how do we standardize? Well, we standardize using this formula before, which should look familiar. We saw this last unit, or the first set of notes we did for the first test. This is that z-score calculation. We talked about z-scores and how they measure how far things are from the middle. You know, we said if you're at one z-score, you're only one standard deviation from the middle. If you're at two standard deviations, your z-score would be 2. Z-scores can be negative because it could be below the mean. So z-scores are a way of measuring the distance from the mean, but they actually are also how we standardized. By doing this calculation to any values on your distribution, you turn them into standard scores. So this is the standard score. A lot of people refer to z-scores as standard scores. If you see that, it's because we use them for the standard normal distribution. So again, this is the calculation, and this is how we standardize any variable x. So if you have a number x, you want to standardize it, you subtract the mean, divide by standard deviation. And these are the original mean and standard deviation, not the 0 and 1 we just talked about last page, but whatever you start with. And then that'll give you a z-score that will be in this set that has 0 for the mean and 1 for the standard deviation. So for example, this is a curve that's not standardized. So the mean here could be anything. It could be 5, 10, a million. It could be, whatever. And the standard deviation is not, standardized. It's not 1. It's going to be whatever. It could be 7, 12, whatever. And what they'll do is they'll take the values of this, subtract the mean, divide by the standard deviation, and they'll get values that will make it a nice standard normal curve. So this one, again, has mean 0, and the standard deviation is going to be 1 up or down. Any value on this is going to have that calculation done where you subtract the mean divided by the standard deviation to make it a value on your standardized normal curve. Again, so properties of the standard normal curve, because we're going to spend a lot of time with the standard normal distribution, we'll do a lot with it. The total area is 1. So the area under this curve, all this is 100%, right? 1 or 100%. When you think of 1, you should think of 100%. So 100% of the values are under this curve. Now these tails go on forever. They can go further and further. But again, as they go out, it gets really rare. There's not very many values out here. So the percentage out here is really small. Most of the percentage is in the middle. So it does extend in forever in both directions. So it extends forever. It doesn't actually hit the x-axis ever. Again, notice it's unimodal and symmetric. So again, it's got that nice symmetry. This symmetry is a really important thing to remember. We kind of saw this last section with the 68, 95, 99.7 rule, that empirical rule. This symmetry is helpful. It's helpful for these guys as well. Almost all of its area is between -3 and 3. So almost all, not quite all, but almost all is between -3 and 3. So most of the values we care about are in this range. We usually don't care a lot about the stuff down here. We just got to remember that's not 0. It's not empty on the ends. There is still values out here, but most of the values are in the middle. Okay. Now, like I said, we don't want to do calculus. So one nice thing about having a standard normal distribution is someone went and did the calculus for us and created a table that tells us the different areas. And this is called the standard normal table, or you might call it called the Z table, because it finds the z-scores or uses the z-scores to find areas. So it's going to have two sides. It's going to have the front side and the back side. The front side is going to do positive z-scores. So you'll notice here these are all positive z's. These are the z-scores. Now this is just the first decimal of the z-score. So what you do is you actually take the first decimal you want. So say I want the number 0.14. Well, then I find 0.1. There's 0.1. And then the second decimal is on the top. So 0.14 is right there. So now to find the area left of the z-score, instead of having to use calculus, I just find the entry on the table that corresponds to 0.14, and it's right there. So 0.5557 would correspond to a z-score of 0.14. If I had 0.26, so there's 0.2 and here's 6, then I would go to that value because I have 0.2 and 0.6, and so it would be this 0.6026. So you're using the first letter, so these would be the first decimals, and these are the second decimals. We're not getting any more precise than that because if we need to get more precise than that, then you're going to have a bigger table. In that case, it's when you start using technology if you want to be more precise. So this is just kind of a quick cheat for someone that needs a value, but they don't have to be super precise. But that's the idea. So this is the positive side. because these are positive z's. So z is positive. And again, notice that this chart is finding the area to the left. So it's only finding the area to the left. So when I did that 0.14 and found that 0.5557, that is the area to the left of 0.14. If I want the area to the right, well, I just subtract from 100 or 1, because remember 100% or 1 is the whole thing. So if you take away the area to the left, you'll get the area to the right. But that's the idea. So this chart always gives us area to the left. Important thing to remember the whole time you're working with this chart. You want to remember that the table is always giving you area to the left. That was the positive side. The table has two sides, and this is only part of it. I'll show you the whole table here in a second. But the other side you'll notice is they're going to be the negatives. This is going to be values below 0. So these are going to be negative. So now instead of trying to find, area to the left of the positive value, z-score on the right, we're going to find the z-score that's going to be on the left, and we're going to find the area to the left of that. So notice now that these are negative numbers. So these are still the first decimal. It gives you a whole number here just because I picked this as like the end of the table, so it starts at negative 0.3. It would have a negative 0.09 or 0.9, a negative 0.8, negative 0. If I just use a different piece of the table, which I'll show you. But these are the first decimal still. And again, to use this, you have your first decimal, and then you'll use your second decimal. So will be up here. That's going to be your second decimal. So like if I want to find negative 3.42, there's a value right there. This one's pretty small, 0.0003, but that's because negative 3.4 is going to be way over here on the edge, and so there's not going to be very much left to the right of it, to the left of it. So you can see as you get further left, this is going to get smaller and smaller. That's why these values are pretty small, because these are all negative 3 point something. They're way far off to the left. Again, so you have the full table, and this full table is available in my lab, my math lab, or my stat lab. It's called my math lab for algebra, and I always say the wrong word. But so my stat lab has this full table. It's got the positive z-scores and the negative z-scores. I will provide this with your exam for the next exam so that you can use it. I will show you ways to use a calculator instead, and you're definitely welcome to use the calculator because you don't need to use the table anymore. This is one of those things where we developed this back before we had fancy calculators, and so it still hangs around, and a lot of people use it. Some people are more comfortable with it than the calculators, but if you get comfortable with the calculators, then the table does become kind of not needed, and you can just skip it and just use your calculator, and that's fine. But for now, I'm going to introduce the table first, and then we'll talk about the calculator here in a minute. So here's the negative side, right? So you can see how these are negative values. You can see this one goes all the way down to -0, so I could have negative 0.0. And then there's the second decimals are across the top. So if I want to do a number like negative 2.45, see that? So negative 2.4 and then the 5. I would just find where those cross, and there it is, negative 2.45. To the left of that is 0.0071. Not very much, because again, negative 2.45 is pretty far over. So there's not very much left over when you get negative 1, 2.5 almost over this way. So that's why it's only 0.0071, which is 0.7%. That's really small. But these areas, these in the middle, these are areas. These are the areas. And on the top and the side are the z-scores. It even has an example down here. Shows you like if you want to find the z-score negative 1.645, that corresponds to an area. So if you go negative 1.6 and then 4.5. Notice with 4.5, that's somewhere between 0.04 and 0.05, because if I do negative 1.645, well, that'd be kind of halfway in between, and that's why they put it right there, because it was halfway between. It's an important value we find a lot, so that's why I put it on this chart, so you'll see that. Same thing with negative 2.575 is another kind of common one. So they did negative 2.575, which is halfway between the 7 and the 8, ends up right there. So those are kind of some common ones. That was the negative side. You have the positive side, has the same 1.645 and 2.575 on the bottom. But again, you just use this if I want to find the area for 1.13. So there's the 1.1, there's the 3, and I just find where they intersect. So the 0.3 comes down here, the 1.1 comes here, and so I see that 0.8708 is the area to the left. That's like 87%. That's what that tells me. So 87% is to the left of 1.13. So that's that normal distribution table. I'll probably use it in the notes every once in a while. But again, as we go, we'll kind of get more into the calculator too. When you do this, you're going to be finding areas to the left a lot, which that's usually pretty straightforward because you just do it as is because the charts are already to the left. So you just find the area to the left, you're done. Sometimes you want to find area to the right. Remember that you can always find this by finding the area to the left and subtracting it from 1 or subtracting from 100%, right, if you're dealing with a percent. So that will give you the area to the right. Sometimes you find the area between. So the trick here is you just find both these scores and you subtract the left one from the right one. Because if you subtract this area from this area, you're just left with the stuff in between. So that's why they took Z2, the whole thing, minus Z1, subtracted this piece, and then you're left with the between. So those are the three main things you're going to do. You're going to do, you're going to do left, right, and between. Because when you're looking for areas, you're looking for these percentages, probabilities. You usually look for the percentage that's below a number, left, above a number, right, or between two values, and that would be your between. Those would be the three main things we do. Okay. Let's do some calculations now. Now that we kind of know how to use the chart stuff, let's do it. So first we want to determine the area under the standard normal distribution that's left of a z equals negative 2.25. So again, since this is a negative, I'm going to go to the negative side of my z-score, so it's got the negatives. I want negative 2.2, so I'm going to find negative 2.2 there first. And then I want that 5. So negative 2.25. So I'm looking for the 5 over here. So we can see that this one, negative 2.2 and 5, meets up there. So that's going to be negative 2.25. So the area to the left is going to be 0.0122. So from the chart, the area is going to be that 0.0122. So again, that area is the same thing as percentage or the probability. So there's if you turn this into a percentage, that would be 1.22%. So 1.22% of the results are going to be left of negative 2.25 on this standard normal chart. So again, left of means we're taking this z-score chart and we're putting a value down here, and I get 1 or 2.25 because it's to the left of the middle. The middle is always 0 with the standard normal distribution. And we're finding the area left of, so we just found a small part. So this is the area that's 1.2, the 1.22% or 0.0122. So again, I made this look kind of big because, but really negative 2.25 so far over. This is really small. That's why it's only like 1%. So I probably should have made it further over just to make sure it's really little. The majority of the area is on the right side. And let's do another one. Let's do right. Now we're doing right of 0.83. So if I have a distribution, so 0.83, notice is positive. So remember, 0 is in the middle. So this thing is going to be over here at 0.83. And we're looking for the area right. So we're actually looking for this piece. So notice that this is actually going to be small because instead of looking to the left of a big number, we're looking to the right of a big number. There's not much left because most of the stuff is in the middle. Remember, the middle contains most. There's 0 in the middle. This is going to be most of the data. There's only going to be part of that over here. I think it's still bigger than our first value, but it's going to be different. So here I'm going to look at 0.83. So I'm going to go to my positive side of my chart. Positive side, 0.83. So I find 0.8 and then my 3, so 0.83. I bring the 3 down, bring the 0.08 over, and I see that it is 0.7967. So 0.7967, 0.7967. So the chart, remember the chart gives us the area to the left. And this is asking for the area to the right. So we actually just found this region. So to find the other piece, this is where we subtract from 1. So we're going to take 1 minus 0.7967, and that will take away this part, and leave us with just this piece over here. So if we subtract that, we get 0.2033. So this actually has 20% here. So the area here, is 0.2033, or 20.33%. We'll do a lot of decimals, so my math lab and my stat lab and stuff will be looking for the decimal. For both of these, the decimal would be the answer. the percentage is just to show you what that means. So this means that 20% of the values in this data set are on this side, whatever data set it is. Last one, let's do between. So let's do between. I'm going between negative 1.101 and 0.56. So first off, let's find the area for this one, for the negative 1.01. So I'm going to go back to the negative side and find negative 1.0. So negative 1.0 is all the way down here. And then we're doing 1.01. So I do 1.01. So I bring my 1 down to right there. And there it is, negative 1.01, which is 0.1562. 0.1562. Let's find the area for the next one. This one is a positive, so we're going back to the positive side. It's 0.56. I'm going to find 0.5 and then a 6. 0.5 and 6. And so then we're going to come down here and over here, and we find that that one is 0.7123. So 0.7123. 0.7123. Now because we want between, we're going to take the bigger area, always the bigger area, and subtract the smaller. So we're going to take that 0.7123 and subtract the 0.1562. So when you're doing between, you always take the bigger area minus the smaller area. You should get the bigger area from the more positive one. You know, the negative one should give you a smaller one. They could be both positive, both negative, but in that case, you just use the bigger number goes first. You know, again, always the bigger area first. And when you subtract them, you'll find the area between those two values. I'm going to do this in calculator because I want to do this in my head. So 0.7123 minus 0.1562. And that gives us 0.5561. So we have 55%, you know, okay, this would be about 55.61% between. That's what that's telling us. So 55% is between the two numbers. Okay, so that was doing it by hand. And I know it seems silly because you're like, I gotta have a calculator. Why should I know how to do it by hand? One of the important things about doing it this way is knowing about what you're looking for. You know, that we're making this distribution. We're marking off the values, like this is negative 1.01, and this is negative 0.56, and be able to tell that you're looking for this region between, and then figuring out that, you know, you're taking a z-score and finding an area, and you're figuring out that this area is 0.5561. Knowing things like positive numbers should always be on the right, negative numbers should be on the left, because with these z-scores, the middle is always 0. That stuff is really important. So I'm glad we kind of showed that here. Hopefully you kind of keep that in your head as you're going, and that you think about that with how these z-scores work. Because when you get to the calculator, it's really easy to type numbers in a calculator and get an answer that's wrong because you didn't type the right values in. But if you're not paying attention, if you're not being careful, you might miss that. So if you stop and think about how these z-scores work, what you're actually doing, like this, sometimes you can kind of catch those mistakes. But yeah, we're going to do the rest with a calculator. From here on out, if you want to, you can use a calculator. I might show both sometimes, but you can always use a calculator for this. So if I want to find the area on a z-score, I'm going to use the function normal ZDF. Then you're going to have to enter some values. So this is kind of built for finding the area between. So it's always going to ask for a lower limit and an upper limit. So it's basically asking for this kind of situation. What's the bottom number and the top number? Now you can get by with this and actually find the other ones, the to the right of and the left of. If you just make the other limit, so like this one, we'd have the left limit would be like really small, like negative 1 billion. Because if you do that, then you're going so far out that you basically got this whole area. Because again, as you get past -3, you're really, really, really small. Or if I wanted to find the area to the right here, I just make 0.83 the left limit, and the right limit I just make 1 billion. You're really big. And that way I've got enough, because once you get really far out there, the rounding and stuff, you're kind of okay. It's okay if you round off a little tail at the end. So your lower limit, upper limit, you'll put 0 for the mean, because remember the standard distribution always has 0 for a mean, and 1 for the standard deviation, because that's the standard, deviation for the standard distribution we're working with. If the lower upper values, I'm not going to use like negative 10 to the 99th. That's going to be like negative 10 billion, or use 10 to the 99th for the upper. Your calculator might not like them this big, so if you need to, you might do like negative 10 to the 50th or something. But if your calculator will let you just do negative 10 to the 99th, that's just really big. That's all I'm doing. I was just checking a really, really, I should say big, but small, really small number. Negative 10 billion is really small. It's just, to me, it's a really big number, but just in the negative direction. or you put in 10 to the 9th and really put in 10 bit, 10 bits is a really big number. Note that we're not going to really ever use PDF. Just like we saw last section with the binomial PDF and CDF, the PDF, it just finds for a single value, and that's really not very useful because we're always going to find ranges. We're going to always find the area between two numbers or past a number. We're never going to find the area just under 0.83 because just that one single line, that's kind of a silly area to talk about for this like vertical thin line. So we're really never going to use PDF. We're always going to use CDF, and you'll see that as we go. So okay, let's do this once with the calculator. So again, we look at this, we look for our left variable. So left is going to be this one because it's the more negative one. And this is positive, so it's going to be the right value. So it's going to be our left limit or right limit. I should say lower and upper. And then again, the mean is going to be 0 because we're doing a z-score standard distribution, standard normal distribution. And the sigma, standard deviation, is going to be 1. So when we type this in, we're going to get the normal CDF. We're going to type in the negative 2.56, the 1.45, the 0, and the 1, and then close it. Now, some calculators you type it in just like that. So if you have a calculator that's not very fancy, you'll just type it like that. Mine, you'll see in a minute, is kind of fancy, so it does this a little bit for me. So I'm going to hit second distribution. So it's the same distribution button we were using for the binomial PDFs. This time, though, it's right up there in the top. I want the CDF, not the PDF. You know, it puts you on the PDF first, but we don't use that. We use CDF. Hit enter, and so you can see here how it's letting me type values in. So here I'm going to type in negative 10 to the, sorry, I'm doing negative 2.6, negative 2.56 for my left bound. Hit enter. I'm going to type in 1.45 for my right bound. We got 0 for my mean, so I'm going to type 0 for my mean, and 1 for my standard deviation. So 1 for standard deviation, just like that. Hit paste, and so then it types it out for me. So again, it depends on how fancy your calculator is. You might just have a calculator where when you hit the button, it just might go to this screen, and you might have to type those numbers, and it won't tell you what they are. Mine's just so fancy, it tells me what numbers I'm typing. But you always want to do it that way. You always want to do lower, upper, the mean, and then the standard deviation. Commas in between to separate the numbers. Once you type that in, it'll give you an area. So this will always be a value less than 1, right? Because this is a percentage. You know, this is 92% or whatever. This is less than 1 because 1 would be 100%. And this one makes sense because you can see how I'm going from really far to the left. So if I do a little distribution here, notice that negative 2.56 would be pretty far off to the left. And then the right one is 1.45. That's going to be pretty far over to the right, 1.45. So that's why it's going to have most of the value in between. So in this area in the between is the 92.12%. I rounded that, but that'd be the area in the middle. Again, if I move the decimal twice, that makes it the percentage. So my answer for this one is 0.9212. And MyLab will ask you what to round to or tell you what to round to. So they'll give you like 3, 4, whatever decimal places. So just be careful about 90. That'd be the decimal version. That'd be the percentage version. So 92% of the data is going to be between those two values. So that's how we use the calculator. So again, we're going to hit second, and then this distribution. The DISTR stands for distribution, which makes sense because we're working with distributions, right, with the normal distribution. And we want normal CDF, not PDF. We want CDF. If your calculator is like, well, you could just type in those values. A lot of times 0, 1 will just be in there from last time, so you'll be fine with that. You have to change the top two values. And that's the idea. You know, if you don't have it like mine, you know, yours you'll have to work like this, where it'll basically give you a screen with just the normal CDF like that, and so you don't have to sit here and type in the values and type in the commas like this, and then type in 0, 1, mean and standard deviation, close parentheses, and there you go. It looks like that. So you can do it like that, if you don't have the fancy calculator that is what mine does. Okay, let's try a couple more with that. Before I get into those, I want to talk about another idea or something that's going to come up a lot later on. So, I'm going backwards now. Yeah, so that was taking the z-score and finding the area. We also go backwards. So that's the big thing here. So now we're going to take find the z-score for a specified area. And this will be something we do a lot. So a lot of times we'll want to find a specific z-score based on certain areas. Sorry, this one's working backwards now. So we're going to work backwards. They're going to give us an area, and they're asked us to find the z-score that corresponds to that area. So a lot of times I'll call the area alpha. Now, this is a Greek letter alpha, and it's used for the area variable a lot. So when I'm talking about an area that I don't know yet, we'll just use alpha. And if we were working with a z-score that has alpha to the right, we use this notation right here, z alpha, z sub alpha is what you would say. So z sub alpha or z alpha. That's going to be a quick way to reference a z-score that has that area alpha to the right. So it references the z-score that has an area of alpha to its right. So note that z alpha has an area of alpha to the right. Big thing here is the fact that it's to the right, not left. So when you're working with this notation, you'll see it. And instead of alpha, sometimes they'll give you the area. They'll say z of 0.5 because it wants 50% area to the right. And then you find the z-score that corresponds to that. That's what z with the little sub number or whatever stands for. Alpha is just the generic variable, but a lot of times will have a value. So like z of 0.25 or 0.5 has area of 0.25 to the right. That's what that means. So because it's z sub 0.25, z sub 0.25 has an area of 0.25 to the right. So like this area would be 0.25 if that was a z of 0.25. And it'd be a z-score that has that much area to the right. Okay, so let's do this now. We want to find the area, the z-score. We're going to find the z-score given the area. So they said find the z-score given the area under the curve to the left. Notice they'll have to tell us which area, whether it's right or left, is 0.86. So if I draw those distribution, you see I do this a lot, so I make sure I'm thinking about it correctly. Say I think 0.86, that's a good percentage of the area, right? That's most of it. So I'm going to think it's probably going to be over here, right? Because 0.86 is going to have 86% to the left. It's going to be most of the area, right? There's only going to be a little bit left because 0.86 is like 86% out of 100. Well, 86 out of 100 is pretty much most of it, right? So this area is 0.86. We're looking for the z-score with 0.86 to the left. So I'm not going to call this z sub 0.86 because it doesn't have 0.86 to the right, it has 0.86 to the left. So we're looking for that z-score. Notice, first off, that this z-score is going to be positive, right? Because we know that 0 is in the middle and has 50% on each side. Well, this one has 86% to the left. So it's going to be more than 0 because it's going to have more than 50% to the left. Now, that's how you can always tell. If something is percentage is more than 50% and we're talking about to the left, well, it's going to be over here to have more than that. If it was 86% to the right, well, that would have had to be over here and go that way. But because this is 86% to the left, it's going to be bigger than 0, so it has most of the values over here. Okay, so I need to find this. Now, we can use our table to do this. You can actually do this with a table. So I'm going to show the table, and then we'll talk about the calculator on the next page. To use a table, since first off, I know I'm looking for a positive z-score. I'm going to go to the positive side of my z-scores. And I'm going to look for 0.86 as an area. So instead of like a z-score right now, I'm looking for an area because I'm going backwards. So 0.86, you'll notice, is not exactly on here. There's no exact 0.86, right? I got 0.8621, that's fairly close. 0.8599. So what I'm going to do is I'm actually going to look for the closest value. And in this case, the closest value is 0.8599. Because you see how closely that rounds up to 0.86 or 86%. This one would round down to 0.86, but it's a little bit further off. This is only like 10,000th off. This one's like 21 thousandths off. So this 0.8599 is going to be the one to go with. I'll get 0.859. So I use the chart. Find area 0.8599. And then we'll use that to get the z-score. So 0.8599 has a z-score 1.08. So the 1.0 is the beginning for 0.8599, and then 0.8. So it has a z-score 1.08. And because the chart is already to the left, straightforward, right? We're done. That is the value. That's what they're looking for. It's a z-score. So z here is 1.08 because that will have a percentage of 0.86 to the left. It's a little more complicated when we go to the right, which we'll see in a second, because that's what our next problem does. So our next problem wants us to find the value of this. And they don't say find a z-score, but remember that this notation here means find z-score with area 0.25 to the right. Remember, that's always to the right. It feels backwards because our chart goes to the left. This tells you to find 0.25 to the right. So if I think about the distribution, I want 0.25, which is small, right? This is less than half, right? So I'm going to put it over here. I want this piece to be 0.25. And we're looking for that z-score. So we call this z sub 0.25 because it does have 0.25 to the right. Well, the trick here is that instead of actually using the 0.25, we're going to use the opposite piece, this piece here. Note that if this is 25% of the data, well, this one's got to be 75% or 0.75. Because together these have to make 100% of the whole thing, right? So this one, we just do 1 minus 0.25. And that's how we get this 0.75. So we can actually look up 0.75. So look up 0.75 on the chart. So on the chart here, notice I'm still on the right side, so I'm still looking for positive numbers, right? Because when I drew this, it kind of helped me remember that this is on the positive side, because 0.25 to the right is going to be over here. 0 would probably still be kind of in the middle here, be 0. So 0.75, look up 0.75 on the chart, so look up 75%. And 75, it looks like it's between these two, 0.7486 and 0.7517. I think 0.7486 is just slightly closer, right? Because that's going to be like a 14 off. If you add a 14, you have 75. Here, this is 17 over. So this one's going to be just a little bit closer. I'm going to look at this value, 0.67. This will be my result, 0.67. If you get a 0.68, it's going to be fairly close, but 0.67 is just a little bit closer. So we get the z-score of 0.67. So 0.67 had 75% to the left. 0.67 had 75% to the left, which means it had 25% to the right. So that's why this is the correct number, because it has 75% to the left, so it means that conversely it has 25% to the right. Okay, one more thing. And we'll do one more with the table and I'll show you how to use the calculator. We want to find two z-scores that divide the area under the standard normal curve into a middle piece that has 0.95 and the two outside pieces that have 0.025. This is like breaking it into 95% in the middle and then two edge pieces that both have 2.5%. Because note, if you take 2.5%, so that's what this is, 2.5%, two of those is going to make 5%, and that'll be the rest of the chart. So it's going to look like this. It's going to be a distribution that looks like this, where it's got a piece over here and a piece over here, so that this piece and this piece are both 2.5% or 0.025, and then the middle piece right here is going to be 95%. So that's what it's breaking it into. We want to find the two z-scores that do this. Remember that this does have symmetry, so there's a little nice symmetry down the middle, 0. So because this one is 2.5% and that one 2.5%, they match, these two z-scores are going to be those opposites, because they're going to be basically corresponding. One's negative because it's on the left, one's positive because it's on the right, but they both should have the same kind of area on the away from them. So you have to be the same distance out to make them the same shape. So these z-scores are going to be similar, but they're going to be opposites. That means we don't really need to find both. We just need to find one. I think the easiest one to find is the one that is to the left, has a 2.5% to the left, because that one, we can use our chart that works to the left. So we're actually going to find this one. So find z for 0.025 to the left. Because once we know this score, which will be a negative, right, because it's on the negative side, then we can just flip that and get the positive, and we'll know this score. So let's find the negative one, and then we'll flip and get the positive. So I want 0.025. So we'll look at the negative side now. I'm doing negative. 0.025 on my chart. So 0.025, there it is, right? So if I make sure I'm doing that right. Oh, no, 0.025. I went too far. 0.025 is, where are you? There you are. 0.025 is right there. That's what we want. That's the area we want. So what's the z-score? Well, the z-score is negative 1.9, negative 1.96. So negative 1.96 has an area of 0.025 to the left. So negative 1.96. From the chart, z equals negative 1.96. Now that's this z, right? So this z is negative 1.96. That means the other z, this one over here, is going to be the corresponding one. It's going to be positive 1.96. So the other, because of the symmetry, right? This is based on that symmetry. No zeros in the middle. So this is negative 1.96, has to be positive 1.96. The other z is 1.96. And that's the way to do it with the chart. If you have the percentages, you can always go back and find those z-scores. Remember, the zero is always in the middle, negatives on the left, positives on the right, and you can find those z-scores using the chart. Now, what if I want to do it with the calculator? So that's the last thing for this section, is just to find the z-score if you have an area using a calculator. To do this, we're going to use the operation inverse norm. You'll find this under that distribution button again. Note that the inverse norm specifically works for area left of the value. So it's kind of like your chart. It only works with the area left. So when we're finding area left, that's what we do. Now, how do we make it so it works find the area right? Well, we saw that when we did the last page. If we want to do the area on the right, we just subtracted the area that was on the right from 1, and then we used the area on the left. So we can do that here as well. So if you're going to do area to the left, you just leave it as is. Area is A. Area is going to be A. If you're going to do area to the right, then you do 1 minus A. And that's how you get the area to the right. And then 0, 1, that's going to be our same mean and standard deviation. That's what these are. Because we're doing these normal curves, these standardized normal curves. The mean's always 0, and the standard deviation is always 1. So all that really changes is the area on here. We do an area to the left, just use the area. If you're doing area to the right, you gotta subtract 1 from the area. Okay, so let's try it. Let's find a z-score with an area of 0.12 to its left. So this is the area to its left. Since it's left, we can just leave it as is. We don't have to change it. So to do this, we're going to do inverse norm. I guess it's norm is capitalized, parentheses, and then we're going to have the area, which is 0.12, the mean, which is 0, and the standard deviation, which is 1, and that will give us our answer. So we're going to go to that second distribution button again, so the distribution button again. You'll see that option 3 is your inverse norm. So it's called inverse norm because inverse in math means opposite, so it is the opposite of doing the normal, the first two functions, because instead of finding the area, it actually takes the area, goes back and finds the z-score, so that's why I call it inverse. Okay, so what's the area? Well, the area we wanted is 0.12, right? That's what they gave us, 0.12. And then the mean and the standard deviation are 0 and 1. Put that in there. Again, you might have to type it this way. You might just do inverse norm. You have to type the area 0.12, 0, 1, and then it'll work. But it should give you the z-score. And notice this makes sense as a z-score, not an area, right? Because area is always going to be less than 1. This is a z-score because it's beyond negative 1. So this would be a z-score, not an area. So this is an area, negative 1.17. The z-scores we don't usually tend to worry about going too much more than like 2 decimal places. So that's going to be good. My stat lab, again, will specify how many decimal places, but I think typically they're like 2, if I remember right. Let's do one more. This one, again, they're using that notation. Remember that this means area to the right equals 0.72. So this notation, again, that 0.72 is area to the right. Okay, so to do that, we're going to do 0.72 to the right, so we're going to take 1 minus 0.72 to find the area to the left, which gives us 0.28 as area left. So we can use the inverse norm now with that subtraction and put 0.28 in there. And then 0 and 1 for our mean and standard deviation, just like before. So since this 0.72 is to the right and this inverse norm only works with left, we had to find 0.28 first. So that's what we're doing. So we do the distribution, distribution, inverse norm, 0.28, 0 and 1, and it will give us our value. Now you can see how getting these values, so we got negative 0.58. When you get these values, the calculator just spits them out. So if you didn't draw your distribution and think about what you're getting, it'd be really easy to get this wrong. Like maybe you forgot to subtract from 1 like this. So it's very helpful on these to draw the little distribution and think about what's going on. So I think about this having 0.72 to the right. So I would think, okay, more than half is going to be over here. This is going to be 0.72. Because if I didn't do it right, I might end up with 0.58 being positive instead of negative. But we know because our z-score is going to be over here with most of the values to the right, because 72% of the data is on the right, it should be a negative because 0 is in the middle. And so this number should be a negative. If we get a positive, we know we did it wrong. So that's one thing we should figure out. Same thing up here. If we did this problem, we should be able to draw the little distribution and think about 0.12 means the left. Well, 0.12 is not very much. So that's going to be a small piece, right? 0.12 area, 0.12 down here. So the z-score for that is going to be a negative, and we did get a negative. So that's one reason why it's helpful to do it by hand a little bit, or at least draw the picture by hand, because then you can stop and think about, should the z-score be positive or negative? Because if I show you this last one, if we do this one with a 0.72, if I go back and change this to a 0.72 instead of 0.28, you notice we get the exact same number, but we get the positive. And so it looks like it's right. You know, hey, that's an error. Yeah, it seems like it's right until you stop and think about what's happening here. Think about that 72% has to be on the right, and the value z needs to be a negative. This is something that's really important to be able to think about the rest of this this couple next chapters leading up to our second test. You got to be able to think about these areas like this. All right, so that's it for chapter 6, section 6.1. We're going to spend a lot more time with these z-scores and these normal distributions. So you see a lot of these pop up throughout the rest of the semester. This normal CDF and this inverse norm are going to be functions that we will use all semester long the rest of the semester. So I really recommend you get comfortable with those on your calculator because we will use them a lot. It's a good idea to keep drawing your little pictures so you know what's going on as you're going, when you're doing homework and stuff. Have a little notebook or a scratch pad, kind of write those out so that you know what you're doing, but also know how to type it in your calculator. All right, I'll see you on the next set.